On behalf of BIC Magazine and our sponsor, Maestros, I'd like to welcome everyone to today's webinar on how to maximize asset uptime by implementing a non-intrusive inspection program. This is Robin Dupree from BIC Magazine. First, a few pointers regarding your webinar console. You can maximize or reduce the size of any of the windows. At the bottom are widgets to access resources, including a PDF of the slides. Click the middle green icon. There is a Q&A box to text in questions anytime during the presentation, and this section of the webinar will happen at the end of Russ's presentation. If you experience any technical problems, click the yellow question mark. I'd like to thank our sponsor. Maestros is a leading one-source global provider of technology-enabled asset protection solutions used to evaluate the structural integrity of critical energy, industrial, and public infrastructure. Maestros asset integrity management programs enable plant operators to maximize the life cycle and productivity of their critical assets and facilities. And now it's my pleasure to introduce you to the presenter. Russ Davis is Maestros Group Asset Integrity Management Services and Mechanical Integrity Center of Excellence Manager. He has more than 28 years in asset integrity program development and implementation. His experience includes pressure vessel, above-ground storage tank, and piping inspection, testing, and evaluation. He has an extensive background in process safety management, including hazard assessment and consequence evaluation. He has developed and directed asset integrity programs for a global chemical company with facilities in North America, South America, Europe, and the Asia-Pacific region. He has also served as an owner-operator and external consultant for the implementation of asset integrity programs. And now, I'd like to hand the mic over to Russ.
Good afternoon, everybody, and thank you, Robin. And thank you very much, BIC Magazine, for hosting this. I want to talk about something that's very near and dear to all of our hearts, everybody in the mechanical integrity, operations, management, maximizing uptime. And one good way to maximize uptime, reduce risk, is to perform non-intrusive inspection, or as API 510 refers to it, externals in lieu of internal. This is all risk-based type inspection, and it's based on a full understanding of the damage mechanisms that can occur that are detrimental to our equipment. Non-intrusive inspection, or an external in lieu of internal inspection, as we all know, pressure vessels are traditionally inspected at 1/2 the remaining life based on corrosion rate, or every 10 years for an internal inspection. This inspection is, of course, very expensive, and it's inherently unsafe. You're putting someone in a confined space area, you're putting someone into a situation that they really, in most cases, don't need to be there. It's dangerous. We have years and years of incidents that have occurred that tell us, you know, if we don't have to do this, simple enough, let's don't do it. We've got good backup from a recognized and generally accepted good engineering practice, such as API 510, National Board Inspection Code, and just within the last few years, that Norsky Veritas, or DNV, has written an RP, G103, that has addressed this same type of inspection, or what they're calling NII, non-intrusive inspection. And then our Canadian brothers, obviously, it's being accepted over in Alberta with AB 506. They allow the non-intrusive inspection, or external in lieu of internal inspection, when the external NDE, or the external inspection services, provides data as good or better than that provided by an internal inspection. The NDE technology has progressed very, very much in the last few years, or throughout the life of it. I started in this business really almost 30 years ago, out in the field, and the NDE that we had then, I don't think I would have said that, well, I'm going to do an external in lieu of. But today's NDE, non-destructive testing, non-destructive examination, is much more definitive. It's much more comprehensive, and in some cases, in my opinion, is as good of or even better than an internal inspection, and it's inherently much safer. By safer, it also eliminates the need for emptying, cleaning the vessels, for the degassing, for the blinding, for the internal surface preparation, and then for putting personnel in the vessel. You minimize or eliminate a lot of scaffolding needs, just all of the costs that go into it. Back years ago, when I was looking at this as a real alternative for a client that I worked in, we looked at vessels that we had gone in multiple times. Every 10 years we've been going into them, and the service was non-corrosive, the service was non-detrimental, and every time we went in, we were able to see everything real well. It was always clean, and we could see even the fitters write-up still on the wall before we left, before we did an internal inspection. Cost on that ran us anywhere from $10,000 to $15,000 if we didn't have any hazardous waste that needed to be disposed of. So the cost reduction is significant, and again, I go right back to that safer, reducing the risk to personnel. But there are rigid requirements to assess a vessel for non-intrusive inspection. The results to give you a better understanding of what damage mechanism may adversely affect the vessel. The inspection plans for non-intrusive inspection are targeted, and they're typically better defined. And the results in time and resource saving obviously are huge advantages for non-intrusive inspection. Now, there are disadvantages to non-intrusive inspection as well. One of the things is, you can't inspect trays, you can't inspect demisters, you can't inspect downcomers, you cannot inspect weirs, you cannot inspect the pass plates, you can't inspect any of that. So if there's another reason or an operational reason or production reason that you need to go on the vessel, then non-intrusive inspection is not a viable option. You don't have a visual record of the internals. And I know to some of us and some of us old school people, we like to see it. We want to know what it looks like on the inside. So, that is a drawback. But if I'm looking at what the pressure boundary looks at, if I'm looking at the integrity of that vessel, it's obviously a good option. External inspections may not detect surface indications. Now, this is a truism. No matter what we do externally, we may not find small surface indications, such as small pitting, such as a small surface breaking linear indication. We may not find it 100% of the time. But we go back to are those indications detrimental to the pressure boundary? And if we can't locate it with the NDE methods that we have today, it's not going to be something that's going to be detrimental to the pressure boundary. External inspections do not typically inspect 100% of the vessel, although visual internal inspections may be limited as well. When you do an external inspection, it's cost prohibitive to do 100% of the vessel. API 581 gives us good guidelines for how to inspect for an effectiveness, and we'll get into that a little bit later in determining the effective inspection methodology. But you're never going to see 100% of it. But then again, I've been in many, many pressure vessels, and there's a whole lot of them that I never see 100% of the wall, or it's never clean enough. You can see where they've cleaned it well, maybe on some various wells, but there's a lot of areas too. Unless you completely remove all the trays, completely remove all the downcomers, you don't see it. One of the other disadvantages is the technical requirements are much more rigid and more detailed than traditional internal inspections. So how do you start? How do you perform one of these? First of all, you got to do an integrity review. It's essential to gather and evaluate background data, documentation on the equipment being considered for non-intrusive inspection. This data includes such things as equipment data, material of construction, detailed design drawings, etc. Year built, past inspection records, operating conditions, all of the records concerning the equipment, such as previous inspection history, any repairs or alterations, and the previous inspection methodologies. We're going to talk in just a minute about effectiveness of various inspection methods. So we need to look back on what was done previously to see if they've even utilized effective inspection methods. Accessibility to the vessel. I can't do a good external inspection on a very hot vessel. We just don't have techniques that will allow this. And the same again for very cold vessels. If I remove a lot of insulation and it's going to freeze up the minute that you do that, we've got an ice layer or something that's going to prevent us from contacting the vessel, then maybe it's not a candidate for non-intrusive inspection. Also, we have to evaluate each zone, such as, let's talk about a distillation column. If I'm looking at a distillation column, I typically look at it at least in three phases. Your liquid phase, your middle hold-up phase where you've got the two-phase liquid vapor flow, and then your top section where you've got the vapor. Many times, these vessels have different corrosion mechanisms. They may have different corrosion rates, that's going to affect that vessel. I'm going to have to be specific about an inspection test plan for each zone of the vessel. And then I got to look at the structural integrity assessment. In other words, the ability of this vessel to withstand damage that's being performed on it, and to what extent. If I have a vessel that was designed with no corrosion rate and I'm already starting to see potential damage or potential wall loss, and any wall loss is going to lead me to a fitness for service or to condemning the vessel and having to replace it, it may not be a good candidate for non-intrusive inspection, or it may be a great candidate for non-intrusive inspection in order for me to make the plan to where I can replace in the very near future. I've got to have the data and I've got to have the NDE, I've got to have knowledge to make that kind of decision. Which brings me to the next one. Should we be doing non-intrusive inspection, in other words, the external NDE, should we be doing that by itself or in conjunction with other inspection methods? This is the methodology extremely handy for pre-turnaround inspections where I can go in, do these same type of inspections, look it over, and then determine repairs that need to be made so that we can go ahead and get the planning done, get the materials ordered, schedule the crews that's going to be there during the turnaround in order to be able to do the repair. Once you've done that, you're going to go through a decision process. The decision guidance process assists in determining whether a particular equipment item should even be considered for non-intrusive inspection. Through a series of questions and an assessment of available documentation on the equipment, certain equipment that should not be considered for NI can be identified. And that goes back to the disadvantages that we just talked about a second ago, is, if I need to look inside of it to check out the trays, check out the weirs, then I may not want this vessel to be inspected non-intrusively. If there's other damage mechanisms or just completely unknown damage mechanisms that I don't know about, that I can't assess with an effectiveness, or I can't perform an external NDE successfully, then it's just not a candidate. So you have to have confidence in the ability to predict the type and location of degradation based on the damage mechanism assessment. Previous inspection effectiveness, and then the severity and rate of degradation. This is just kind of a logic tree going through, how we determine if a vessel is suitable for non-intrusive inspection. just following the logic through it, is kind of what I've just talked about. Once you've selected the equipment, is the equipment intrinsically suitable for non-intrusive inspection? In other words, if I can't get in this vessel anyway, if we do a lot of compressor bottles. I'm not going to do a compressor bottle internally, but I do need to know the integrity of that compressor bottle. Then that's a yes. Has equipment previously been inspected? No. If equipment hasn't been inspected, then I'm going to look, was it designed specifically for non-intrusive? Again, going back to compressor bottles as my example. Is equipment same as others that I have records on? If it is, then I can do the like in kind or the same service type evaluation than NBIC, that the DNV or RP, and that API 510 refer to. And then is entry scheduled for other reasons? Then if I come down to my logic and there's other reasons, then I'm going to perform an internal visual. If I go through the nose over here, you can see on the right side of the screen, then we can come back over to our decision tree. We can apply guidance from our tables within our process, which is this kind of referring to, and then to where you get out to an evaluation that yes, we're going to do a non-intrusive inspection, or no, we're going to go do some more research to determine if it's fully effective for a non-intrusive inspection. The inspection plan, once you've done the damage mechanism assessment, now you start putting together the inspection plan. And this plan is the ultimate objective for a non-intrusive inspection, so we can verify the safe and reliable operation of the equipment, obviously, and to perform inspection in a cost-effective fashion. The inspection plan is going to include when the inspection should be scheduled, how long it will take, inspection methodologies, gathered data precision. In other words, if I'm looking for a quarter-inch crack, then I better be able to use a NDE method that has the sensitivity and the ability to detect a quarter-inch crack. Areas and items of the equipment to be inspected, the inspector's qualifications, equipment accessibility. This goes back to how I'm going to inspect a vessel. If I need to inspect 75% of a vessel and I can only get to 50%, then it becomes a little questionable as to the effectiveness of the external inspection. So we have to be real cognizant when we develop inspection plans of the accessibility. Many of these inspections can be done utilizing scaffolding or rope access, so we have to be able to plan for that, and do we have anchor points for the ropes, or can we actually build scaffold around here without being detrimental to the operation of whatever we're working on? A lot of this is done offshore in the North Sea and other offshore industries, and it's difficult sometimes to be able to put that many people onto the platform. Bed space is always a critical issue, and then access to the vessels becomes hugely cognizant within your inspection and test plan. So the safety requirements is something that has to go into an inspection and test plan. If we have potential exposure to H2S, we want to make sure that our inspection and test plan is comprehensive enough that it's going to define all the safety requirements that are going to go along with working with and performing those inspections. And then whether the inspection will be performed on or off stream. Again, like I said earlier, it's impossible to inspect some very hot, vessels to do it comprehensively or effectively. So those kind of vessels either have to go to an internal inspection, or they have to wait till that vessel comes down during the shutdown just to be able to do the non-intrusive. And in comparison with previous inspections, if the inspection data that I have, I want all of that to be utilized in the development of the future inspection plan. If I've noted potential corrosion under nozzle D, I want to make sure that I get good comprehensive thickness scanning, a corrosion mapping under nozzle D so that I can evaluate the corrosion rate, fitness for service, continuing after what we've inspected. And then cost and time restraints. It would be easy to say, we're going to do the most expensive inspection so that we get the best that we can get. But sometimes that's just not practical. There are costs, there are time restraints that need to be taken in consideration. So what we're going to do is the most effective method in an economical way to look at those vessels to get the best data that we can for an analysis. Then we have to determine the inspection or the effectiveness of inspection methods. And being associated with Mistras, I can tell you over here we have something like 600 plus services. It's very difficult to not have a very comprehensive way of looking at vessels to determine the best, most effective, and efficient methodology for inspecting pressure vessels. You start with the identification of the damage mechanism. A complete understanding of all potential damage mechanisms will identify what type of damage we're going to be looking for. You really only have three major types. You've got cracking, you've got localized corrosion, you've got general corrosion. These are things you can inspect for and inspect for effectively. So, you're going to want to know which one of those are you looking for based on the damage mechanism. And then a review by a qualified subject matter expert in determining the most effective method. This goes back to what I'm looking for, what resolution I need to make sure that I have so that engineering can do an evaluation as to the suitability for continued service. And then we're going to use basically this risk-based methodology. It's all risk-based methodology. And we're going to determine utilizing that RAGA gap or those, generally accepted good engineering practices, and we can select an effective method for evaluating the damage mechanism. And then we're developing an NDE method suitable for that detection and quantification of the damage. Remember, quantification is extremely important. Then we're going to look at extent and coverage. We always go back to RAGA gap again, good engineering practice. API 581 is a really good method or a really good source that we get for what an effective inspection is and for grading that inspection effectiveness. We'll touch on that right now. Right now, this comes out of the D&D standard, and it's selecting an inspection type. In other words, based on the damage that I've associated with that particular equipment item, I want to understand whether it's a type A, where its damage mechanism is not expected to occur, but that an inspection is required to confirm there is no onset of a damage mechanism. A type B would be where the damage mechanism is expected, but with a low to medium progression, in other words, a low to medium corrosion rate, or based on fracture mechanics that I've taken a look at, the progression of any cracking that may be there. We understand the location of degradation can be predicted, and we don't anticipate to impact the vessel integrity for at least 2 outage cycles. So whether that be 5 years, 10 years, whatever we're looking at, we want to know, that we can at least predict that. In other words, do we have a remaining life of at least 10 to 20 years? For a C-type inspection, I'm looking for damage mechanisms expected with high to medium progression, a higher corrosion rate, a higher crack propagation. The location of damage mechanism cannot, with full confidence, be predicted and may affect vessel integrity within 2 outage periods. An inspection is required to confirm absence of critical sized flaws. In other words, if we go to a C-type inspection, then we're expecting we're either going to almost go straight with that data to a fitness for service or to some other evaluation to determine whether or not we need repairs or whether we can run it just to the next outage. Now let's look at inspection effectiveness. And these come right out of API 581, Part 2, Table 2. And by the A, B, C, and D, this is your effectiveness ratings. An A inspection would be highly effective, and where you'd say in nearly all cases that the confidence of detecting that by this inspection method would be at least 80 to 100%. And an effective method you would say would be 60 to 80%. And then for a C, moderate effectiveness, you'd say at least half of the time you're going to be able to detect the damage mechanisms that's there. And D, where you have limited or specific effectiveness. And D-type inspections are really something that more or less validates lack of damage with limited specific information. So I can assume, going back to the D&B method of categorization or the equivalent, that you're going to have a type inspection where you're not inspecting to have damage. You can use a more limited type inspection methodology to validate it. So we've kind of taken and putting this together for my engineering group so we can say, okay, what do we do if I need an A inspection, a highly effective, and I have a C inspection type? In other words, I'm anticipating damage. I don't have 100% confidence that I can predict it. Then we can define those inspection methodologies using right out of the tables. We're going to do 100% UT of the total surface area. Selected areas, we'll do 10% UT scanning or 10% profile radiography. This is for general thinning. I better kind of define what I'm talking about here. We've taken a few of the damage mechanisms that are most prevalent, and we've evaluated them so that we can put the effectiveness category plus effectiveness type we're looking at. So moving for general thinning, moving on into an effective inspection, where we are expecting to have that damage. We're going to do 75% of all the spot UT. We're going to do a 5% UT scanning to validate it and to be able to evaluate it, etc. We move from general thinning into a cracking mechanism. This is based on wet H2S cracking, Hick, SOHIC type of cracking, and as you can see, we're utilizing more effective inspection methodologies along with more advanced methodologies in order to be able to detect the cracking. Looking at the C-scan, we're looking at stepwise cracking so that we can determine if there is any Hick there, hydrogen-induced cracking. Utilizing C-scan or topographic type of UT scan, going greater than 90% of the total surface area. For weld cracking in the HAZ, we're going to use a shear wave or a time of flight, or even phased array UT. Phased array UT is a very effective method for determining the integrity of the welds HAZ. And as you can see, the effectiveness goes down in right out of that by a lot of times just the limit or the extent of the inspection that you'll perform. Kind of the process here, once the inspection plan has been developed, we're going to include such things in the inspection plan as how we're going to get the people there, how we're going to get the people and equipment there, mobilization, demobilization needs. We're going to note scaffolding, where we're going to want scaffolding, how much scaffolding, or rope access, whether we can do it that way. we're going to designate a cleaning or what surface prep needs to be there. If we've got paint, whether or not that paint will need to be removed. If the vessel's coated in product, obviously the product's got to be removed, but we're going to define what the surface preparation should be. And then if it's insulated, we need to talk about insulation removal, how much removal, and in what ways. If we have a vessel that we're not inspecting any real internal damage mechanism, we're going to be doing UT point thickness. Maybe we're just utilizing inspection ports located at the most likely area that we would guess if any corrosion was to be found. Now, if we have a C-type inspection where we expect a lot of damage there, then maybe we're going to remove a whole bunch of insulation or all the insulation and do some automated scanning, some C-scanning, some corrosion mapping. We need to look at access needs. We look at all the safety needs. Within the inspection plan, you're going to put in, the need for permitting. Do we need a hot work? Do we just need a proximity permit? And then we need to define when the kickoff meeting occurs so that we're all on the same page. These inspections can be complicated, so we need to make sure that, we're making the plan, we're executing the plan, and then we can evaluate the plan. From the plan, inspectors, technicians need to take what has been planned in the ITP, the inspection and test plan. It needs to be executed 100% to that plan or as close as possible once they get into the field. If our inspectors get into the field or any inspector that gets into the field, should they run into any problem being able to evaluate or being able to perform, execute directly to the inspection and test plan, then they need to be back in touch with the engineer who has defined that inspection and test plan so that we can either make corrective measures, that we can get additional data, or we can just call it if we can't have access, or if we can't remove all of the asbestos insulation, then we need to be able to call that inspection off. So if you can't execute it, we immediately make that determination once the guys have hit the field. Now, once inspection's done, we've got a lot of data. That data comes back, and it's got to be analyzed. We got to determine, first of all, did we execute the plan as designed, and did we do it effectively? Should there be any minor deviations from the actual plan as compared to what was mapped out in the inspection plan? The minor deviation may or may not have any impact, but we have to analyze that. We have to follow up. We have to determine whether there has been a suitable non-intrusive inspection, and we have the data available to do a full analysis and say this vessel is suitable for service for the next 10 years or for a given frequency of time. Just like we would do with an internal inspection, we're going to evaluate the data. Once that individual comes out, we're going to determine next inspection due date, corrosion rates, remaining life, all of that. If there's a significant decrease in what was achieved in comparison to the inspection plan, then further inspection has to, if further inspection is necessary, then an interval will need to be determined, typically by corrosion rate or fracture mechanics. If a fine cracking, it doesn't necessarily mean we got to go repair it, but we have to understand it. We've got to do a fitness for service evaluation. We've got to understand the propagation of cracking in the given material at the given temperatures, etc. And if the actual inspection did not meet the requirements of the inspection plan, then the NII cannot be used as the basis for continued operation. In other words, it needs to be put back on the list to be opened and visually inspected, or a plan needs to be put in place to repair or replace the vessel. Setting the next inspection frequency, extremely critical from what we've got here. Because you can look at the plan, you can look at all the data, you can determine at that point, the total overall effectiveness in the same way we would do when we evaluate any and all inspection methods. Is it suitable for continued service? If I have a remaining life greater than 10 years, then I'll go 10 years. If I have a remaining life less than 10 years, I'm going back to 1/2 the remaining life based on the corrosion rate. Additional monitoring that may need to be determined, such as, should I put on some type of a frequent monitoring of this vessel, acoustic emission, UT thickness, additional phased array, any of these that can be applicable. In some cases, continuous monitoring systems are put in place to where it's mounted on the vessel, it's left on the vessel, and then readings can be taken once a week, once a month, once an hour, whatever we need to do in order to make sure that vessel is safe for continued operation until we can do something else with it. So in the reporting, a complete final report needs to be developed based on the non-intrusive inspection. And this is going to start with, okay, our evaluation of the vessel and whether or not, all of the inspection and test plan, was it executed properly? Here's the data that goes with that execution. Here's the validation of its suitability for continued service, its fitness for service today and in the future. You want to have in all your documentation, of course, the inspection plan, the results of the inspection, test report, and then the results of the evaluation, because this comes, all of the data from the field, like I've said, comes back to those personnel for evaluation to say, yes, we have done an effective non-intrusive inspection. We have done an external in lieu of internal, and we've met the requirements of the code, we met the intent of the code, and it's safe for continued operation for a given frequency. So with that being said, let's go to the questions and answer. Hopefully there's some questions that have come up. Hopefully I can answer them too. Back to you, Robin.
Thanks, Russ. Yes, there are a couple of questions. The first one is, can you use the program to inspect heat exchanger tubes?
No. For inspecting exchanger tubes, I really do not have a good, suitable way for doing a non-intrusive inspection of exchanger tubes, cracking, pitting, wall loss, any of that externally. There's some methods using acoustic emission for recognizing leaks from the tubes, but we really don't have a way to evaluate the life cycle of that tube to tell you whether one tube is good or we need to plug tubes or any of that without opening up a heat exchanger and then inspecting those tubes, either eddy current, remote field, or an iris type of methodology.
Great. And the last question, what is the potential cost savings by using non-intrusive inspection as opposed to traditional internal inspection?
That's a great question. The main thing I want to remind everyone is non-intrusive inspection is a huge risk reducer. We are eliminating confined space entries or minimizing confined space entries when we don't need to. We're having a lot better predictive analysis of our vessels. But in the other part of that, and we all live in the real world, is non-intrusive inspection cost savings are huge. There is a major company in the oil and gas business, petrochemical oil and gas global company, that is claiming in published literature savings of around $500 million since they started their non-intrusive inspection program. Now that's obviously a huge amount of vessels and a huge amount of facilities, which they have, but their analysis is there's huge savings that go with it. So like I've said, when I did my analysis a few years ago, it's been almost 10 now, but just putting together all of the costs associated with cleaning, clearing, having mechanics on both the vessels, slip the blinds, put everything in place, degassing, cleaning the vessel, scaffolding the vessel, then putting an inspector inside, especially when that inspector went in and came back out in 30 minutes and said, looks good, I'm out of here. My cost analysis was saying that I was spending in the neighborhood of $15,000 per vessel. Obviously, for bigger vessels, that's more. For smaller vessels, that was less. But just on an average, it was around $15,000. And then if I had any hazardous waste that had to be disposed of, that $15,000 could double or triple quickly. And that was a few years ago. Now, when we start talking about offshore industry, obviously those costs go way up just because of transportation, bed space, just everything that goes into the complexity of the offshore industry. And I didn't take into account there either the off-stream time. When you take a vessel out of service, you can bet almost 3 days of non-productive time. And in some cases, that means the whole unit is down. If I can do a non-intrusive inspection while the unit is up, while I don't lose any production, obviously there's huge, huge savings involved.
Well, thank you. That concludes our presentation. And thanks, Russ and Ms. Russ, for sponsoring this educational content. And we'd like to remind everyone that you can visit them at mistrussgroup.com. The recorded version of this presentation will be available in about 2 hours at bicwebinars.com. Feel free to watch it again and share with your colleagues. On behalf of all of us at BIC Magazine, thank you. Have a good day.